Okay, let's get started, y'all. So, before we get started, important announcement, we have an exam coming up a week from today, March 27th. The paper version will be in class on March 27th, and the coding part of it will be in lab on the 28th. So, Wednesday, March 28th will be the coding portion, and the paper version will be Tuesday, March 27th. And the format will be the same as it was for the first exam. So for the paper version, the material that will be covered will be up through what's presented on Thursday. So it will include the linked data structures that we'll be going through today and tomorrow. The material that we will test will be since the last midterm, but obviously you need to be conversant with material that was presented before the last midterm. And the paper version will focus more on conceptual knowledge plus perhaps very short programming type problems, maybe some debugging, some design. It's certainly going to involve being able to select an appropriate data structure given a scenario. So for example, if I tell you that I need to do a range query and do find, insert, and delete efficiently, then I would want you to select a map or a set for that rather than a hash table or a vector or an array. So that will be on Tuesday. Then on Wednesday, right now my guess is there will be 2 coding questions, probably one on lists, the second one on sets and maps. And you'll be using Code Assessor like you did for the first exam. And like on the first exam, for the coding portion, you will have a 1-page cheat sheet front and back. You will not have any notes for the paper version. And there are already a sample midterm up, as well as from Dr. Plank, so I would strongly encourage that you go through those. I'll also make sure that in the next day or two that for the coding questions, that those coding questions are up and available so that you can work them on Code Assessor. So any questions about that? Yes?
So on the write-up for the lab, like lab 7, it says that it's like, on the actual lab papers, it says that it's due like Wednesday at 6 a.m. But like on the write-up, it says due after midterm too.
Mm-hmm.
So is it due like, do you mean like after the paper portion, like the in-class, or the...
So it is probably, let me take a look because it is probably right now sitting right, my guess is the due date right now is between the 2 of them. Yeah, that's not going to give it to me. Yeah, I see that. So I'll tell you what's going on there. The lab is already extended because of the midterm. So it really ordinarily would have been due earlier. So I'm really not wanting to extend it. If anything, it should have been due like Sunday rather than Wednesday. So let me think about that. Maybe I'll put it due on Thursday. I can't push the deadline though because of the way things are. So I might set the deadline at least for it to be Thursday. But I'm not going to push it any further than that because it's not really a 2-week lab. So what was the other thing I was going to mention? probably on the I'm going to consider on the coding portion, I may make the exam for the coding portion be an hour 15 minutes rather than 2 hours. The reason is that it really shouldn't be taking you 2 hours. If it is, you probably you're missing something, okay? What I'm concerned about on the coding portion is that you primarily get the logic correct. And if every little I isn't dotted and T isn't crossed, I'm not so concerned with that. Some of you know that. You got a 0 from Code Assessor on the first midterm, and then you got something like 18 out of 20 because your logic was right except for some super small thing. So what I've been noticing is a lot of you will just keep pounding away on Code Assessor, but the logic, if you haven't gotten it within, say, half an hour or 45 minutes, you're probably not getting it. So I'm probably going to set the coding portion at an hour 15 and have the TAs go over the lab for the remaining 45 minutes. And I think that will work better because I remember last time some students saying we really didn't have the TAs going over the lab and that hurt us. So that's the other thing is I'll probably make it an hour 15 for the coding portion. And like I said, you should be able to finish it in that time because in the past you would get the paper version and you were expected to do both the paper version and the coding part in an hour 15 minutes. Okay? So you're really getting extra time as it is for the coding portion. And when you go to 302 with Plank, take a look at his exams. You will get essentially the same thing I'm doing, except you'll finish it in all of it in an hour 15 minutes. So you are getting extra time. Okay. Next thing, programming tip. Because I am seeing some issues with pointers. So with pointers, remember that we make a distinction between what we call stack allocated memory and heap allocated. So stack allocated is the memory that gets allocated when you call a function. It's stack frames. So when I have something like main blah blah blah, call A, and over here I have A blah blah blah, and I have some variable. I'm going to give you two variables for A. I'm going to give you a, pretending this is from the code processor lab, I'll give you prize X and prize star Y. So when main gets called, it gets some memory on the stack. And then when A gets called, it gets some memory. And X and Y both are what we call stack allocated at this point. Now, X is an entire prize. So X consists of whatever a prize object is. And that is considered stack allocated because it's on the stack. But Y is just a pointer. Right now, it is nothing. It's not even null. But it's only 4 bytes or 8 bytes for a 64-bit processor. And in order to give it an object, you have to allocate it off of the heap. And the way we do that is by saying Y equals new prize. And now Y is pointing to a prize. And this prize is heap allocated. there's a big difference between stack allocated and heap allocated when it comes to memory reclamation. When A returns, this stack frame gets popped, and all stack allocated memory goes away. So in particular, the memory for X, that prize is reclaimed and it goes away. But heap allocated memory is not reclaimed. It stays out there. And in this case, we have what is called a memory leak, because nothing points anymore to this prize. And therefore, it cannot be reclaimed. It's like you littered, like you simply threw something on the side of the road. And if you litter enough, just like the environment gets polluted, your program space will get polluted, and eventually you'll run out of memory. So it's very important that you remember to reclaim heap allocated memory when there are no pointers to it anymore. Okay? So in this case, if you were not going to use the memory associated with this prize anymore after A, before it returned, you would have to call delete. And by calling delete Y, you would remove the object that Y points to and give it back to the memory allocator, back to the heap. Okay, so a memory leak, let me define it because it's important. I know I did in an earlier lecture, but I'll do it again. A memory leak occurs when you lose the last pointer to a heap allocated object and the object has not been deallocated. Okay? Now, I'm seeing a big problem with memory leaks in code that I'm looking at, because many of you are still not sure when something needs to be initialized or not. So for example, in the last lab, I saw a lot of code that looked like this. Bitmap BM equals new bitmap. BM equals M copy. This is a memory leak. Can anyone tell me what the memory leak is? Yes. This bitmap no longer has a pointer to it. Okay, so the first statement caused BM to point to a new bitmap. The second statement reassigned BM to point to M copy, whatever that returned. As a result, nothing points anymore to this thing. It's a memory leak. Now, you certainly could insert a statement 1A that deletes BM. But what's wrong? Why isn't this really efficient? What's the net result of 1 and 1A? They cancel each other out. So there's no reason for 1 and 1A. All you need it to do was just not allocate the the bitmap to begin with. So this is important, and if you do this on an exam, I will deduct points because memory leaks are important. Okay, just like littering is bad, littering your program with unused memory objects that you forgot to deallocate is bad practice. And also, you don't want to allocate stuff you're never going to use, which is what was happening before. When I said BM equals new bitmap, I never even used that bitmap. Okay, so you really need to become comfortable with understanding when you have to initialize something and when you don't, because it's going to get assigned something else before it's ever used. In this case, saying BM equals new bitmap there was no point to it because the very next statement you initialized it with the object that it was really going to use. Okay, in fact, if it really bothers you, you could have just combined the two statements and said BM equals M copy, which would have also worked. Okay, so I really want you to be aware of memory leaks and prevent them. You have to clean stuff up. That's the point of the destructor in Lab 7, is when you deallocate a code processor object, you have to manually deallocate anything that was allocated off of the heap. Okay, so it's just stack allocated is automatically reclaimed, heap allocated, which is anything that you create. Do you remember from the pointer labs, anything that's heap allocated was created with what? Pardon? No, okay, but actually stack allocated ones also, no. Okay, I'll actually say, constructors do not actually create objects, they initialize them. An object is already created when the constructor gets called. New. New is what allocates heap allocated objects. So if you allocated something using new, then at some point you need to deallocate it using delete. Nothing allocated using new will ever be automatically reclaimed. Okay, so anything you allocate with new must be reclaimed with delete. Okay? So my final thing is, if you're having trouble with pointers, and a lot of students do, what I try to do is give you different ways of thinking about pointers and stack allocated objects. So here's today's way of thinking about it. There's many ways of thinking about it, but you can think of a heap as like a bunch of balls. And they have numbers on them, which are their addresses, 25, 31, 88. Those are their addresses. And when you ask for a ball, and it's a pointer, what you get, so maybe it's a ball, and I have a pointer P, what it gets is the address of the ball, the number of the ball. Okay? Like in this case, if I said maybe I get 25, so P is going to be 25. So it gets the address or number of the ball. Whereas if it was stack allocated, let's say this was the stack frame again, this was main, and this was A, this was X, and this is, say, P now. P is 25, whereas X may actually be the ball 31. Actually, I shouldn't say 31. X is just a ball. So stack allocate, and you'll see that it's like, in this case, the ball is in the box. So when you throw out the box, okay, when I heave the box, everything in the box gets thrown out. Okay, so X, which had a ball, that was automatically thrown out. But anything outside the box, which is 25, 25 is outside the box, 25 is not thrown out. The only way you, quote, throw it out is with delete. Okay, so that's another way of thinking about pointers. It's like a number on an object. When you allocate something off of the heap, you get an address. It's like a number that identifies the object. But it's outside of your stack frame. And when you toss the stack frame, that object still lives. Whereas anything inside the stack frame goes out with the stack frame. Just like with a collection of items in a box, when you throw out the box, everything in the box gets thrown out. Okay? So questions about all this? Okay. So moving on, we are kind of moving to a third part of the course today. So I'm going to actually move back. So the first part of the course up through February 6th was about a review of C++. It was constructs you'd seen before, so we were reviewing them and going into more depth. Then, over the next month, we've looked at a number of data structures for finding, inserting, and deleting and doing it efficiently. So we looked at hash tables, we've looked at lists, we've looked at double-ended queues, we've looked at sets and maps. But we haven't looked at how they're implemented. We've looked at how to use them, at their APIs. Now, with hash tables, we looked at how to implement them. But thus far, with lists and sets and maps, we haven't looked at how they're implemented. We looked just at how you use them at the API. Okay, and we talked about their running times using big O notation. So now, starting today, we talk about going under the hood. We're going to look at how are these data structures actually implemented. And that's essentially going to be what we look at for the final 6 weeks of the semester, is how we implement lists, which we're looking at this week. Then, after the midterm, what we're really looking at is how we implement sets and maps. And that starts with recursion and then continues on with something called trees. But both lists and sets and maps are implemented using something called linked data structures. They use pointers, which we introduced late last month while I was out of town, and now we're coming back to them. Okay? Before, you kind of needed to know about pointers because they were pointing to objects that you would store in a map or a list. But now, we're actually going to use pointers to implement a list. So for the next couple of days, we're going to talk about how we use pointers to implement lists. And we're going to start with the simplest possible data structure, which is a stack. And I know in the book starts with lists, and then it goes to stacks and queues later, which is why there's a bit of jumping around in the reading assignments for this week. But a stack is actually a simplified list, and so we consider it first. Now, you've seen stacks before with vectors. In fact, in the real world, we implement stacks with vectors. It's more efficient to use a vector or an array to implement a stack. But they can be implemented using lists, and since it's easy to show, to kind of introduce you to lists using stacks, that's what we're going to do. So a stack is often called a last in, first out data structure because the last item in is the first item that you take out. So for example, if I had a stack of dishes, right, and I was stacking them, say, after washing them, I'd add them like that, and I'd end up with a pile of dishes. Well, normally, what dish do you remove from your pile of dishes? The top one. So that's last in, first out, because the last dish you put in is the first one out. Okay, obviously that's not how we implement grocery lines or teller lines or a traffic light. That would piss a lot of people off. But there certainly are situations where stacks come in handy. Your pile of plates or a pile of trays is an obvious one. And there are two basic operations associated with a stack. The first is push, where you add something to the top of the stack, and pop, where you remove the top item from the stack. So it's very simple. You're always dealing with one end of your data structure. And that's why vectors are so efficient with stacks, is you're always adding at the end and subtracting from the end. So we are, however, going to be looking at how we could implement them using a linked data structure. So we're going to have our public API, and you see push and pop. Those are the two basic operations. Empty, returning whether it is empty or not. And again, Dr. Plank is old school, and he's using an int. Okay, I generally prefer that you use a bool, but he is going to use ints when he talks to you in 302. So I'm just again pointing out that C++ tends to use bools for their flags, but old school is to use ints. And then we have a constructor and a destructor for the stack. So the destructor always has a the destructor always has a ampersand in front of it. I'm just trying to get rid of this. How do I get rid? There we go, trash can. Okay, so a destructor always has that, come on, always has this ampersand in front of it. Okay, and the destructor is always called when the object is being reclaimed. It's called by delete. It's also called when the object is deallocated off of the stack. Okay, so here's just a quick, easy example with a stack. What he's doing is he's reversing a file. So this is something he's going to use as an example throughout the notes. So basically, see if we can, basically if he had a list that was give him 6, then what he wants to do is reverse it when it's printed out. So it'll be 6 him give. For those of you who don't, does anyone know what the phrase give him 6 is from? It was, come on, you can do better. No one remembers this iconic announcer? John Ward. So this was John Ward's iconic announcement whenever a Tennessee Vols scored a touchdown. He would yell into the microphone, "Give him 6!" And he did it better than me, but he was always very excited. Okay, what does what does Kessling use? Come on, there's some football fans here. What is Kessling? He didn't go with give him 6. That was John Ward. Kessling says into the checkerboards. Okay, so that's Kessling's call phrase. So clearly not as memorable as John Ward's give him 6. Okay, so at any rate, most of the examples in this particular set of notes involve reversing a file. So you read them in and you print it out in reverse order. A stack is really good for that because with a stack, you read in give, it goes at the bottom, then you read him, then you read 6, And now if you pull the things off of the stack, last in, first out, it will come out in the form 6, him, give. Okay, so here's the code. While you get a line from a file, you push the line onto the stack. Then while the stack's not empty, you pop the stack. A super simple reverse program, 2 lines. Pretty cool. Okay, so let's look at the implementation as a linked data structure. So what we're going to do is we're going to use such a thing called stack nodes. And you should get used to this use of the word node. It's jargon. But normally we talk about an element in a list or a tree as being a node. In a hash table, what did we normally use as the name for an entry in a hash table? Bucket. Okay? So that was the jargon for hash table. For a list or for a tree, the jargon is a node in that data structure. So in this case, the node consists of the string. So this is the value that we are storing. And this is a pointer to the next element. Okay, so each node in the list will consist of, in this case, 2 values, a pointer and a value. So here you see our stack, what we want to construct, and you can see the list. So we have a top pointer that points to the top element in the list, and then 6 points to the next element in the stack, which is him. And him points to the next element in the stack, which is give. And there's no element after give. Give is the last element, so its pointer is null. If you remember, null is a predefined constant. All capital letters. If you print out its value, does anyone know what its value prints out? 0. Okay? But we don't use 0, we use null because it's easier to read. So top is a value in the stack object. The nodes are in yellow. Okay? So we call in effect, we call the stack thing a container. This is a very common concept that you have an object which is a container. It wraps the nodes. So the stack object is the container, and it wraps the nodes. Okay? So the question is, how do we create this list? This is what we want to get to when we're done with our 3 pushes. Okay? So I'm first of all going to go over how that you might accomplish that. Let's say we're going to push a new node onto the list called now. So we want to push this new node now onto our list. So the first thing we have to do is allocate a node object and allocate it. So this is going to be heap allocate it because it is using new. So we are allocating a new stack node, and then we initialize or assign S as its value, and S is now. So when we do that, S is equal to now, next is currently uninitialized. It's not null. If you think it's null, you'll get into trouble. Okay, it's garbage. Whatever used to be there is what's there now. So this is kind of the get a new node and initialize it and set its value. So that's step 1. Step 2 is to start to link it into the list. And we want it to point to the previous top object. So the previous top object was 6. and we want to make now point to 6. The way we do that is by setting its next pointer to be equal to top, because top currently points to 6. So by setting new node next to be equal to top, we make new node point to 6. Okay? So this makes new node points to the previous top element. And finally, we need to make top point to new node. So it points to the new top of the list, which we do by saying top equals new node. So top now points to new node. And we have now linked new node into the list. So if we go to top, top goes to now, next goes to 6, so it's been linked into the list. So that's push. Okay, if we look at the code for any questions about that. Okay. So if we look at the code, you see we have a pointer. This is our first step, so this was step 1. This was step 2, and this was step 3. So that's just the 4 statements that you saw just now. Yes, Drew?
Quick question. Just when you declare stack node, pointer new node, and then you call new node equals new stack node, could you just do all that in one line? Or
Yes, you could.
Okay.
Okay. So Drew's question was, could I just say stack node new node equals new stack node and do that all in one statement? And the answer is yes. Then I would get rid of that.
Okay.
That would be fine. No problems with that. If you do that in your lab, that's cool. Okay. So questions about this, very simple. Notice there's no delete statement here. Okay, we aren't reclaiming the object to which new node points. If we were to delete, if we were to call delete here, that would be really bad. Okay, it would be really bad because we would get rid of new node while we still wanted it in the stack. Okay, so you have to know when to reclaim memory. You can't just slavishly always reclaim memory at the end of a function. In this case, this would be a horrible mistake because we still want new node at the end of this function. In fact, the whole point of this function was to create this new node. Okay, now you may be thinking, okay, but Dr. van der Zanden said at some point I need to deallocate this memory. Pop will do that. Okay, so pop is going to remove the top element. So in this case, we're going back to our original stack, so we don't have now on it. We're going back to our original stack, pretending that that push never happened. And we're going to pop the top element now. So we need to remove the top element, which you can see is 6. We want to return its value, and then we want to delete the object associated with 6. So the first thing we do is, well, let me show you something that could be wrong. Okay, the easy thing to do would be to say delete top, return top S. Okay, actually, that would have a whole bunch of problems. First of all, so tell me, if I just said delete top, return top S, what's an issue with the code you see here? Very good. If you delete top, then when you try to return top, I deleted the object. Top no longer exists. So this is going to potentially get you a seg fault. Maybe, maybe not, but top doesn't exist anymore. So you can't do that. Plus, if you delete top, you haven't yet updated top. You need top to point to the next element. So before we do anything with top, the first thing we do is we save its value into a variable called old top. So we're going to make top and old top point to the same object. So save top is what step 1 is all about. Okay, then in step 2, we're going to update top so that it points to the next element in the list. So that is, I could have said top equals top next. Dr. Planck chose to use old top next. It doesn't matter. Old top points to 6. Next points to him. So when we set top to be old top next, we've set top to point to him. So that's this statement right here. We also need to save the return value because once we delete this node, once we delete this one, we no longer can access the value field. So we have to save the return value. So that's what the second statement is so the first statement, make top point to the next node. In the list. And the second statement is save the return value. Okay, RV stands for return value. And finally, when we've done all that, we have removed 6 from the list because top now points to the next element. So 6 has effectively been severed from the list. Now, and only now that we have severed it from the list and we have saved the return value, is it safe in step 3 to delete that node. And that delete statement reclaims the memory that was allocated in the push function. So there's the symmetry. The new was in push, the delete is in pop. Okay, you do something similar in the code processing lab. So with the code processing lab, sometimes you create a prize and then sometimes you redeem a prize. When you redeem a prize, you need to delete the prize because it's no longer available. If you haven't, you might want to go back and look at your redeem prize code because if you don't delete the prize there, you have a memory leak. Okay, so usually the function where you call new is going to be different than the function where you call delete because usually the function where you call new is all about creation and bringing something new into the world, whereas deleting is about no longer needing the object, and typically that's in a different function. Okay, so if we look at pop, any questions again about this? Okay, so if we look at pop, there it is. We save the current value of top. We sever the node from the list and save its return value. And finally, we delete it. And then we return whatever the return value was. Now, you will notice this piece of code up here. You have a special case. That special case occurs when our stack is empty. So we can't return anything from an empty stack. So if top is null, we print an error message, and in this case, exit the program. Now, that means there is something that has to be done in the constructor, which is we must set top to be equal to null. We must initialize it. Just like integers don't get initialized to 0, or chars don't get initialized to an empty char, or bools don't get automatically initialized to true, pointers don't automatically get initialized to null. You have to do that explicitly, so I'm doing that in the constructor. You can see the implementation of empty is very simple. It simply checks to see if top is null. Now, there is one final issue, and that is the deallocation of the stack. When the stack is destroyed, you need to make sure that you return all of the nodes to the memory allocator, to the heap. So when the stack is destroyed, it might still have some nodes. So when stack is destroyed, you must return its stack nodes to the heap. And the way you're going to do that is by iterating through your list and one by one returning those objects to the heap. Okay? So you have top, and it points to something like, say, give him 6. So what we're going to do is, while top is not equal to null, we need to delete a node because there's still an existing node. So if top is not equal to null, we know there's still another node. So the first thing we need to do is save a pointer to the next node. So we're going to make a variable called next. We're going to save a pointer to the next node. Once we have saved a pointer to the next node, it is safe to call delete to delete that node from the list. And that's not enough. We then need to, with the final statement, right here, top equal next, we make top point to the new top node of the list. So we had to save that pointer to the next element because when we delete top, we lose that pointer. So we had to save it. Okay, so top is not equal to null. So again, we are going to set next. What will next point to after the first statement? After this statement right here. What will next point to? Who? 6. Very good. It will point to 6 because top currently points to him. Him's next pointer points to 6. So top next points to 6. So next is going to point to 6. So again, we can delete him, which is what top points to. And top now is made to point to this final element. Now when we set next equal to top next, top points to 6. Its next field is null, so next is going to get set to be equal to null. And again, we will delete this element, so it goes away. Top is made to equal next, so top is also now going to equal null. And our list is empty, so we drop out of the loop and we're done with our deallocation. Okay? Questions about that? So cleaning up is really important. And Dr. Planck points out that you could have done it even simpler by using some existing calls. So you could have said, while not empty, pop. But that would be less efficient, first of all, because you're making function calls, and function calls have overhead. You have to create a new stack frame. You have to save state information. When you're done with the function call, you have to pop the stack frame. You have to save a return value. So there's overhead associated with function calls. Plus, empty has the overhead of always checking to see whether the stack is currently empty, but we know if it's not empty that the stack is not empty, so that's a wasted operation. So this is a slower, while it's simpler code, it is slower. Okay? So that's a stack. Questions about the implementation of the stack? Okay. So let's then take a look at queues. Remember, queues are like a line, like a grocery line, a teller line. We say that they are a FIFO, or first in, first out, because the first item in is also the first item removed. So we add items in a queue. If this is our queue, actually, and this is, let's not do it yet with, let's not use an implementation. Let's just use the conceptual. We have a line of people, and I am horrible at art. Okay, so this is the front, and this is the back. So when we add something to a queue, someone comes in, where are we going to put the person? Back. So insert at the back. And when we remove something, we remove it where? From the front. So we remove from the front. Okay, so unlike a stack, removal will be from the front rather than from the back. Okay, so let's look at the way we set up a queue. With a queue, we're always going to have the pointer point to the person behind you in line. Okay, so think of the way to think of it is we point to the person behind us. In this case, I'm going to say the item behind us. So not the person in front of us, but the person behind us. And the reason is, when I'm removed, then I can point and say, okay, that's the next person to be served. Okay, so I add it. Give is the first item I added. So this is the front, and this is the back of the list. So give him 6. Give is at the front, 6 is at the back. And we actually have 2 pointers now, a first pointer that points to the front and a last pointer that points to the last or back item in the list. And the reason we do that, why do we need both a front and a back pointer? What if, for example, we just had a front pointer? How would we have to add someone to the back if all we had was a front pointer? We'd have to go through each element in the list. We'd have to iterate all the way through the list, which would make it an order n operation. So to make it fast, we have to have a pointer to the front of the list, which will make it easy to do remove. Okay, so front is for remove operations. And back is for insert operations, to make them efficient. Okay, and a queue cannot be easily implemented using a vector. There's clever ways to do it, but the obvious way of removing an item from the front would require everything to be shifted one item to the left. So we're no longer in a situation where you could even easily implement a queue using an array, at least not efficiently. Okay, so the operations are somewhat similar when we pop something off of the queue. So we'll go over pop first. We're going to remove the first item of the queue, which is give. So when we do that, it should be pretty clear that we need to make first point to the next element of the list. We need to remove the first item, and we need to save the return value. Okay? So again, just like we did with the previous one, we first save the return value. So basically, we're saving the node state information. Save the return value and save a pointer to the first element. That's step one. Step two is to make first point to the next element, point to the second element, second item. So first equals old first pointer. Okay, so this is old first points to here. Its pointer points to here. So when we set first equal old first pointer, it makes first point to the second item in the list. Okay. Now we have saved its value and return value. We have made first point to the next item. So this item is now severed. It's no longer in the list, so we can go ahead and delete it, which is what we do in step 3. We delete old first. That's step 3. Now he's also keeping size. He could have done that with the stack as well. He just added another operation which is going to keep track of the size, so he's going to decrement the size. Okay? Now, there is a special case that needs to be considered. Okay? What if pop is done when there's only one item in the list? So let's say that there was only one item in our list. So we have first and last, and there's only one item in our list. Okay. Well, it's fine to set first equal to first pointer because first will get set to null. And it's fine to delete it. Okay, so when we're done, first will be equal to null. Does anyone, though, see a problem at this point? So this is our list. Has no elements.
Can it be called as a list?
Pardon?
Can it be called as a list?
It still can be called, we still need to be able to call it and add items to it. But there's an issue that here.
Is last one?
It's not very good. Last is not pointing to anything. We say that last, this is a different issue that arises with pointers. We say that last is a dangling pointer. So a dangling pointer is a pointer to a object or an object that has been deallocated. And this is one of the most pernicious types of errors because now that the object has been deallocated, it may very well get reallocated, say to another list. And now last actually might point to something that is in another list. And when you go to add something to this list, you might actually end up adding it to that some other list. Or you might segfault. If it has not been reallocated, then you just might get an error because the C++ will detect that you're trying to access a piece of memory that's not been allocated. There's a whole bunch of issues that come up. So dangling pointers are very dangerous. Okay? They lead, like I said, your program might not segfault. You might just all of a sudden start seeing items ending up in another list. When you do insert, they might end up in a totally different list and you're like hitting your head like, how can these items be showing up in another list? Well, the reason is you never reset last here. Okay? What should last be set to in this case? Null. So if you are deleting the last element of a list, you also need to remember to set last equal to null or you will have a dangling pointer. Okay, so that is, if we look at pop, that is what we are doing. So first thing we do, we check to see if the size is equal to 0. We could also check to see if first was equal to null or if last was equal to null. All three of those would be fine checks. Then we do the code that you saw. So we save the return value. We save the value of first. And we make first point to the second item. Right there, and then we delete the first node in the list. This is the statement I was talking about. We check to see if first is equal to null. If it is equal to null, then we set last equal to null. Okay? So that is pop. Questions about pop? Okay? So push, I'm going to do is go through the steps with push, but probably show you the code next time. So with push, we're adding a node at the end, just like we did with a stack. So it's actually going to look a lot like the code did for a stack. We're going to allocate a new Q node right there. Then we're going to assign an initial value to it. And we're going to set its pointer to be null. And the reason we do that, this is different from a stack. When we did it with a stack, we had it pointing to the item below it. But now it's pointing to the item behind it, and there is no one behind us. So we have to set the pointer to null because there's no one behind me. Then we normally are going to set last. We need to make whatever last is point to this item. So normally we're going to say whatever last currently points to is going to point to new node. So whatever last points to, we want it to point to this new node. That's what we're doing right here. So we're setting this pointer to point to new node. Okay? That's what happens right here. It now points to new node. The problem is, what happens if this was an empty list previously? If the list was empty, what was last? null, which means that this statement right here would segfault. This statement right here would segfault because last is null. So we have to first check to see whether this really says, was the list empty? If the list was empty, then we actually need to set first to be equal to new node. This is the opposite of the pop, where we had to set last to null. Now we need to remember that since the list was empty, first also needs to point to this new node. Otherwise, so in this case, if the list was empty, we don't need to relink we don't need to make the last node in the list point to the new node because there was no last node. Okay, so there's a different action depending on whether the list was empty or not empty. And then after we have linked the new node into the list, the final thing we do is make last point to that new node, and we increment size. Okay, so I will show you the code for push next time, but actually I have showed you the code. It's right there. So it's just going to be an enumeration of that code. Next time we will go into doubly linked lists, which are the hardest one and which you'll do in Lab 8.